Hello everybody, this is Alan Folmsby here in Maui, and today's physics theory is about the Lenzs-Pauli Exclusivity class of phenomena. So I'm going to explain what Lenz's law is and what the Pauli exclusion principle is. Then I'll tell you about there's other things that are related to that same geometry of the inside and the outside. So I just want to tell you about Lenz's law first in magnetism. If you wanted to create a magnetic field, you'd get an electromagnetic coil, for example, and you'd run current through it, and you'd get a magnetic field. Now, if you had a second inductor coil like that, then when a magnetic field induces a voltage in that second mutual inductor, the current runs through it, and that makes another magnetic field change in the second inductor. The direction of that new field is opposite to the first field of magnetism. Lenz's law defines only the direction of the second magnetic field. What I'm saying is that there's Faraday's law and there's other Ampere's apparatus and things. Now Lenz's law is only about the direction that a new magnetic field appears to oppose the initial magnetic field. And I'm going to talk about that in terms of pairing and the pairing of a proton-electron and the non-crossing theory, which I've discussed last week. Lenz's law is due to the deterministic pairing of the proton with an electron. And this pairing is defined elsewhere, but basically it has to do with velocity, relativity between them. And that there is only two dimensions, so it's deterministic, like the pages of a book are flat. And you can connect the top right corner with the bottom corner, and that always is the same two corners, are always connected because of these layers. And to define Lenz's law, you should draw a line connecting each proton and its electron. And then the electron eddy currents are known in electrical engineering, for example. And there's also the proton co-eddy currents, and I'm invoking them as a paradigm for this new explanation using geometry. Lines never pass through each other unless there's an ohmic cycle that occurs. Now, an ohmic cycle, everyone's familiar with resistance and how many ohms there are in a resistor. And a cycle is when an electron gets unpaired and then paired up with a new proton. So the ohm has abstract units of measure called cycles per second. Frequency, ohmic cycles per second. So 1 ohm is equal to n ohmic cycles per second, where n is the scaling factor so that voltage equals IR. Superconductors do not impair an electron from a proton as often. And the superconductivity is rather like an iron nucleus where there's a proton current running without resistance. Now, a superconductor will have a lamination circuit. Now I want to show you a picture in a minute of that lamination circuit, and so I'm going to go over to the camera here. All right, so it's December 29th, I believe. Let me check my calendar here. No, it's December 30th, 2019, 10 a.m. in Maui, or 8 p.m. in London. Hello there. Now, the lamination of these bonds is important because they don't take up any space in one dimension. You could stack up many things. Like I got this flat card in the mail, a Christmas card, and it appears to be flat. And however, just like an atom, it takes up space, even though it's made out of flat things. Watch this. You see, even though an atom may have 10 flat things in it, like neon, 10 protons, 10 electrons. In fact, a neon atom takes up three-dimensional space. Say you're in a vacuum of space between galaxies, and there's only one neon atom per cubic meter. Then radio waves can still go through there. And in one possible theory, a partial vacuum promotes the propagation of radio, but a complete vacuum will only support a photon emitted by those last few atoms before you hit the complete vacuum. All right, I'm going to turn the camera around and show you some of these drawings about flat atoms and Lenz's law and the Pauli exclusion principle. Okay, we're back over to the control panel here, and here we can see the flat surfaces here. What I'm talking about is that there's a proton here, an electron over here, and they're connected by a straight line called EY in this picture, and two other dimensions. So there's two EY and EX, and then a time-like dimension going the other direction. And so this is 2 dimensions of space up this way, and that line makes a flat shape. And these can stack up in laminations quite thick. Now, for a superconductor, you could see in one of these later pictures. Oh yeah, here it is. So if there's a ordinary copper wire, there's a pairing between a proton and one electron, using those 3 dimensions I told you about there. And that as electrons flow along through the copper wire, they have to become unpaired with this one and then paired up with the next one. And that's an ohmic cycle, and that will cause power dissipation. Now, on the other hand, in a superconductor, there is this picture where stacking of these contrasplines, these thin membranes, so that, for example, in proton 5 and electron 5, they're still connected there, even though electron 5 is much closer to proton 6 or proton 7 or proton 8. So they're still connected, so there's been no cycle, no ohmic cycle has occurred in a superconductor. And by the time it has reached this point, there can exist then a proton current where the proton 5 sends its current through proton 6 and proton 7, and a new pairing occurs here without any power dissipation. Just like iron has a proton current. Let me show you the iron has a proton current in rings. Oh yeah, here it is. So iron has 2 rings of protons in green, and there's 12 protons in the top and 12 protons in the bottom here. Let me reduce the magnification on this. Oh, that's a little better, yeah. So this is just the proton nucleus, which is like this 3D model here. So anyway, you see there's 2 rings of protons, green, one on top, and they're coaxial. So that if I turn it around, you see the other ring is not 12 more protons that are touching each other. Now, in a copper electromagnet, these protons are not touching each other. However, there is a proton current going between them anyway, not just the motion of electrons. But according to Lenz's law, the proton and electron move in the circuit together in terms of which ones are paired. the pairing from this proton to the next one, and the one electron may be paired with this one, then the same electron gets paired with this, and as the eddy current of electrons goes around, these protons become paired with that one electron as a superconducting current occurs inside the nucleus of iron. So that's what this picture is showing you here. Those 12 protons in a ring on top and 12 on the bottom, connected to electrons in blue. So you can see over here, this blue thing is an electron. And now the thing is that these 12 electrons are going in a circle around like that, and the line between them is also going around in a circle, like a tornado, a vortex of these red lines coming out. And they have the proton motion pairing is going along with the electron motion. That's the point. These lines are all just rotating around without crossing each other, spinning like a vortex tornado upwards there. And that as electrons move in a circle, so the proton's current moves in a circle. So now I'm going back to talk about the lamination, and that these pair lines have no thickness, so you can stack up a lot of them without losing any molecular strength or anything. So these two dimensions, hx and hy here, go one way out of the proton to the electron, and then a time-like dimension goes the other way into the proton from the electron. And that's what gives a local power and capability to seemingly empty space, is that there's a counterflow and a spin going on. They fill up any vacuum up to about 1 hydrogen atom per cubic meter. And then if radio waves, for example, are trying to pass through the partial vacuum, once they get beyond this perfect vacuum level, the only thing that can be sent out is a photon. And instead of exclusions going on to propagate through these pairs, a photon has to carry on. Now, standard science had been talking about electromagnetic fields for a long time now, 150 years. And Maxwell had the E field and the H field. And those were replaced around 1956 by the vector potential A, and that replaced the electric field and the magnetic field intensity, E and H. They used a matrix algebra for the A vector, so it matches up. It matches up with the gravitational matrix format of Minkowski, but not very useful for us to use for anything quickly. So I've offered an alternative based on the non-crossing law. Standard science doesn't recognize the pairing between a proton-electron with a deterministic line, but I am introducing this, and that's all part of the Particulate Theory of Relativity. Now, the Pauli exclusion principle is different from Lenz's law, which I've been talking about so far. Of course, Lenz's law is about the pair. A proton, electron, it's a little subuniverse, like a cell, one little three-dimensional cell. Now, the Pauli exclusion principle is about excluding those cells from each other. So each pair cannot cross another pair, that kind of thing. For example, in the iron atom, if you had 26 protons, you'd have 26 little subuniverses like springs, and they would not cross each other. They would be rebounding. And now the Pauli exclusion principle says that no two electrons in one atom can be in the same state. They also talk about the quantum numbers, so that no two electrons can have the same quantum numbers, N, L, M, and S, in the same atom. That's the important part. You can see the YouTube video I made of the covalent mock-up from December 27th. Now, the states of an atom include the positions of electrons winding up the line. So I'm going to go back to the camera here and show you some things winding up on ropes, which is a mock-up of reality and accurate in some ways. So imagine at the top of the ceiling is a nucleus, and hanging down are two lines to two electrons. While I'm setting it up, I'm going to start a little video for you. Iron has 26 protons represented here in white and 31 neutrons shown in the dark color. So now also I've shown here the random collection of the same number, 26 white and 31 brown. So if we mix them up at random, we see like the whites touch each other. The protons touch each other no matter how many random tosses of the 57 baryons you give. You'll see that the whites are touching the whites quite commonly in 3 dimensions as you try and put them together. And so this shows that that's a requirement for a stable element like iron. The whites touch the whites. Protons line up with protons. Here are the nuclei of the light elements. Here's the single hydrogen white proton here, and deuterium with the 1 neutron and a proton. And then there's helium over here, and lithium, beryllium. The neutrons all line up next to the protons, and the protons line up with the protons, touching. And the boron, the big absorber, a very good neutron absorber. Element 5. After that, we get the cubes start coming into play. As you could see in the video there, the charge distribution was being discussed. And this has a lot to do with the exclusion of these lines from each other between an electron and proton. So in other words, when the charges were distributed into this iron nucleus in the center of a star during hot fusion, the electron was already paired with the proton. And it was never some kind of ionization into a free electron state. No, always deterministic pairing between each proton in the sun and one particular electron. If iron gets formed, that two-dimensional interaction is what forces the protons into lines of protons. So now here behind me is the mock-up of 2 lines to 2 electrons hanging down from one nucleus on the ceiling. All right, so that was a successful experiment. Now the thing is that this frequency and the quantum numbers have to do with these lines between the nucleus and the electron. For example, when they're hanging away from each other like this, the nucleus can interact with the electrons. However, if they're winding up, now the nucleus is not. So infrequently, the nucleus will resonate. That's why nuclear magnetic resonance is a low frequency 200 megahertz, whereas the electron spin actually, the electron spinning here is much higher, 32 gigahertz. So as you see the electrons spinning around, that's 32 gigahertz quickly spinning. And once they separate, that's one cycle of the nuclear magnetic resonance. Here, once they've separated, then that's the only time the nucleus will directly interact with the electrons along the rope. Once they're spinning, there's an interruption of that interaction. But now, let's bring in a second nucleus on the floor, because so far we've been showing that this is two electrons hanging down from a nucleus on the ceiling. Let's bring in a second nucleus now. Uh-oh, we had an equipment problem here. All right, I'm going to go back to the drawing board for a minute. Stand by. Like this type of a cube here with the 2 by 2 by 2. It has 8 baryons. And then that forms, say, nitrogen, which has the 6 faces covered with the protons and neutrons. So, for example, here's how the cube compares to that. Then we get the heavier. All right, so we just watched that experimental thing with ropes, the string theory of atomic bonding. And I'm just saying that that is geometrically accurate in terms of a line between a proton in the ceiling and the electron down at the bottom, a deterministic string between them which cannot cross any other rope. All right, so anyway, let's move along with the presentation, and that there's no crossing of the ropes, and 2 electrons orbit not a proton, but that wound up line between 2 electrons. And the electrons are spinning around a common centered bundle of these lines. All right, so now I've explained those basics of the Lenz's law and the Pauli exclusion principle. Now, how does that apply to radio, for example? Lenz's law is about the pair, the proton-electron. That's what Lenz's law is about, that as the electron currents going around the electromagnetic circuit, there's also a proton current going around. That can be in an iron. That's true, as I showed you, when the iron nucleus has that proton current going around as the eddy currents of electrons goes around the same direction. And electromagnet also has a proton current going around in the loop, and the electrons are going around the same direction in loops. That's how electromagnets work. And that an ohmic cycle will take place in a radio transmitter as it drives this magnet using Lenz's law, and the pairs of electrons and protons in the radio transmitter are making electrons gather in one place, pushing out by exclusion all other flat membranes. And then the electrons are withdrawn from that place, and bare nuclei are separated from their electrons. And so the Pauli exclusion principle will allow these membranes to come back into the transmitter. Now, radio waves use the exclusion from pairs of protons and electrons in this electromagnet of the transmitter. Once it leaves the transmitter, it is not pairs that are involved directly, but only indirectly through exclusion. Waves of excluded pairs go through the vacuum-like area of the partial vacuum. And exclusion takes place, or if the vacuum is too thin, it will emit a photon eventually. So other examples beyond radio of the LenzPauli exclusion ideas are the free electrons, in which they're only free in one dimension, really, that they're still paired with protons always. Bar magnets, I showed you the proton ring current, how in iron it's going around, and that is the paragon of magnetic circuits. Electromagnets also have proton currents, just like an iron nucleus. And the proton currents have ohmic cycles, as well as electron currents do. And just that the pairing occurs between the protons, pairing changes instead of going through the electron. So anyway, the nuclear charge distribution is an example of this exclusion of and the pairing of, in the iron, the proton to electron forces the charge to form lines of protons. And the final example are the subuniverse exclusion concepts extension. If we consider the atom to be a bunch of subuniverses, that can teach us about our big universe here we're in and how we have excluded all other universes. And keep in mind that in these mock-ups I'm showing, ropes cannot pass through ropes, just like a bond cannot pass through a bond without an ohmic cycle. They spring off each other. And ohmic cycles at cryogenic temperatures are using proton currents like iron. So if, say, take mercury, which at 1 degree Kelvin is a superconductor, the proton currents are just like in iron, in which they're passing between the protons, even though they're separated by atomic distances. Okay, I'm going to check in on my message board here. Maybe people have been talking to me or something. No, it looks like nobody has sent me a message today. Okay, then I'm going to be signing off soon. Thanks a lot for listening. Bye. I'm looking for the button here. Okay, I'm going to sign off any second now. Where's, oh, this, I'm on the internet here, Endstream.